You're on the field. A quarterback launches a perfect spiral 40 yards downfield. The ball arcs gracefully through the air, traveling forward and upward at the same time. How do physicists make sense of motion in 2 dimensions? The secret lies in breaking vectors into components. Today, we're going to master that skill. We'll see how to separate complex motion into simple perpendicular directions. We'll use trigonometry to unlock 2-dimensional problems. And we'll apply it all to analyze projectile motion. By the end, you'll start noticing vectors everywhere in the real world. Our goal is simple but powerful: to describe perpendicular components of vectors and to use coordinate systems to analyze motion in 2 dimensions. Here's why this matters. Real-world motion almost never happens in a straight line. Airplanes bank and climb. A soccer ball curves through the air. People walk diagonally across a room. But here's the key insight. Any vector can be written as the sum of perpendicular components. Think of it like navigating a city with streets on a grid. Instead of saying walk northeast, you say 5 blocks north, 3 blocks east. Same destination, but broken into simpler steps. That's exactly what we do in physics. We break motion into perpendicular directions, and suddenly complex problems become manageable. Let's build the math. Suppose you have a vector with magnitude A at an angle theta from the horizontal. The horizontal component is A cosine theta. The vertical component is A sine theta. Those are just projections onto the x and y axes. And once you have the components, you can analyze each direction separately, as if they were independent one-dimensional problems. Let's try it with a real example. A hiker walks 20 meters at 30 degrees north of east. What are the x and y components of this displacement? Magnitude, 20. Angle, 30 degrees. The x component is 20 cosine 30. That's 20 times 0.866, which equals 17.3 meters east. The y component is 20 sine 30. That's 20 times 0.5, which equals 10 meters north. So our hiker's path is broken into a neat pair: 17.3 meters east, 10 meters north. Now let's work backwards. Sometimes we start with the components and want the original vector. How do we reconstruct it? Magnitude comes from the Pythagorean theorem: square root of x squared plus y squared. Direction comes from the inverse tangent of y over x. Let's check this with our hiker. Magnitude equals the square root of 17.3 squared plus 10 squared. That's the square root of 399, which equals 20 meters. Perfect! Back to the original magnitude. Direction equals tan inverse of 10 divided by 17.3 equals 30 degrees. Again, we've recovered the original vector. Now we're ready for 2-dimensional motion with acceleration. Here's the principle. Treat x and y independently. Each direction gets its own kinematic equations. For projectiles near Earth's surface, horizontal acceleration is 0. The ball keeps moving at constant velocity. Vertical acceleration is -g. Gravity pulls downward with constant acceleration. Combine them, and you get that familiar parabolic arc. A simple set of rules explains every throw, kick, or jump. Let's analyze one. A football is thrown at 20 meters per second, 45 degrees above horizontal. Step 1. Find velocity components. V naught x equals 20 cosine 45, which equals 20 times 0.707, which is 14.1 meters per second. V naught y is 20 sine 45, which is also 14.1 meters per second. So the ball starts equally fast in both directions. Now we can solve separately for time, range, and maximum height. First, the time of flight. Use y equals v naught y t minus 1/2 gt squared. At ground level, y is 0. So 0 equals 14.1 t minus 5t squared. Factor it. T times 14.1 minus 5 equals 0. Solutions: t equals 0 or t equals 2.82 seconds. That's the total flight time. Now, range equals v naught x times t. Range is 14.1 times 2.82 equals 39.8 meters. So the ball travels nearly 40 meters downfield. Next, maximum height. At the peak, vertical velocity is 0. So 0 equals v naught y minus gt. That gives t equals 14.1 divided by 10, which is 1.41 seconds. Plug back into y equals v naught yt minus 1/2 gt squared. Y equals 14.1 times 1.41 minus 5 times 1.41 squared, which is 19.9 minus 9.9 equals 10 meters. So the ball soars 10 meters high. Let's zoom out and review. We've now wrapped up the entire journey of kinematics. We started with displacement, defined velocity, explored acceleration, mastered the kinematic equations, investigated relative motion, and finally unlocked vectors and two-dimensional motion. These ideas formed the bedrock of mechanics, the foundation of physics itself. You now have the tools to analyze real-world motion, from a spiraling football to a satellite in orbit. Motion is everywhere, from the path of a baseball to the sweep of planets across the sky. Physics gives us the language to describe it all. So keep exploring, keep questioning, and always think like a physicist.